All right, everyone. Thank you so much for joining us today. I think we will make a start. So, welcome to our very final live event in our Destination Space series, Ask a Space Scientist. So this is going to be all about you asking us questions. Okay, so you might have met me before if you've been to previous events in this series or other events run by the Department of Physics, but my name is Helena and I'm an outreach officer here in the department, and I'm going to be hosting today's event. So first, as always, just a little bit of housekeeping. So feel free to use the chat at the bottom of your screen. You can chat to us as panelists, you can chat to everybody else, but please try and keep this on topic. Don't share personal details and just be respectful of everybody else in the chat. Secondly, as I already said, this event is all about you asking questions. We want to hear what you want to know. So please type these into the Q&A box, again, at the bottom of your screen at any time during the event, and we will try to get to as many as we possibly can. If you type them in the chat, we might miss them, so please pop them in the Q&A box. You can also upvote people's questions there. So if you have a question, just have a quick look and see if someone's already asked something like it, and then we can upvote those questions to make sure we get to the really popular ones at the top and we're not having to scroll through hundreds of the same very similar questions. That will be really helpful to us. And just to say, we have also, if you noticed on the registration form, we did ask you to submit any questions you had that you thought of at that point. So we're going to get through a few of those as well, but we will do both live and pre-submitted ones as much as we can. Okay, also just to say, we do have a moderator, Nina, who is on the call, who will be keeping an eye on the chat and the questions and making sure everything's working okay there and staying on topic. So if you have any technical issues or anything, please let us know through the chat and we can try and help you as best we can. You might also have noticed that we've got live captioning enabled on today's webinar. You can turn this on or off using the live transcription button at the bottom of your screen. But obviously this is live, so please excuse any mistakes that it might make as we are talking today. And finally, we are recording this event today, and at least part of it, if not all of it, should appear on our YouTube channel very soon. We do have some previous events already up there. I'm working on putting the rest on as quickly as I can. And here's the link to the YouTube channel if you're interested in catching up on any of the past events. Okay, so I think that's everything I needed to go through for housekeeping. So it gives me great pleasure to now introduce you to our panel of space scientists. So if you want to all turn your cameras on, now is the time. So if you've been to previous events, you'll probably recognize them, but just in case you haven't, I'll get them to introduce themselves again. So over to you guys, if you would like to introduce yourselves. So shall we start with Bertie, who's top of my screen?
Hi, I'm Bertie. I'm a second year PhD student, and I'm working on the aerial space mission, which is a mission that is looking to try and detect the composition of planets outside our solar system.
Fantastic. Tris, should we go to you next? I think you're still muted.
Try that again. Hi, I'm Tris, and I was just muted. I'm a researcher at Oxford University, looking at or helping to build space missions that go to other planets to measure new stuff. We've been looking at missions going to the moon and to Mars most recently.
Brilliant. Helena, your turn.
Hi, I'm Helena as well. I'm the meteorite curator at the Natural History Museum in London. I actually recently finished my PhD in the same group as the other three here, looking at meteorites, basically. Yeah.
And last but certainly not least, Katherine.
Hi, so I'm Katherine. I'm also a researcher at University of Oxford, and I study rocks on other planetary surfaces, mostly the moon, doing remote sensing and laboratory studies.
Amazing. So we've got a variety of different areas covered within space science. Okay, so let's kick things off with our questions. So we've got a fun little one to start with from the pre-submitted questions. What's your favorite space movie and why? So should we go in the same order that we introduced ourselves and answer that question, just for a little bit of fun? Bertie?
So I'm going to go for Interstellar, just because it's a movie that really communicated some really challenging and difficult aspects of physics. So it kind of really talked about general relativity and how time does not necessarily go at the same rate for different observers. And when you're close to a black hole, time physically goes slower for you. And then if you were to then reunite with a person who was living at home, they would be far older compared to you. And sometimes the reality of science can be far weirder than some things that came up with in science fiction. So I think this really illustrates that, you know, there's some of the really weird things that can happen in science, and there's a really nice way of communicating some really difficult physics.
Nice. Tris, what's yours?
It'd be The Martian. It was very close to it had a lot of good real science in it, and yeah, I enjoyed it.
Nice. Helena?
So my favourite sci-fi movies are Star Wars, basically, the original trilogy, of course. My very first email address I made was starwarsfreak999@hotmail.com. Doesn't work anymore, so don't email me on that. So I like it because it's not very realistic, but it's a kind of idealized, this is what I'd love it to be like. So not quite as realistic as Interstellar and The Martian, though to be fair, Interstellar has a great soundtrack for revising. I really recommend people for that. So
yeah, I was going to say the same. The Interstellar soundtrack is amazing. Cool. And finally, Katherine.
I have to say I'm just gonna go with general disaster movie because Volcano is my favorite, like, one to watch about a volcano erupting in LA, and it's absolutely ridiculous.
That's such a silly film. It's great.
Yeah, we watched a lot of disaster movies in like geology classes, like after, you know, it's just fun to pick out everything that was wrong. Good time.
Awesome. And my favorite, in case anyone was interested, is one called Contact. It's from the 90s. So if you haven't seen it, really recommend it, because not only is it really cool science, but you get to see the Arecibo, which is now gone, isn't it? Sad.
Yeah.
And not only is it a really cool sort of science story, but it also explores the interplay between like religion and science and politics and science and all of that sort of thing. So I think it's really cool. And also being a woman in science, because the lead is a female scientist, and it touches on those things really nicely too. Cool. So that was the fun icebreaker question. So moving on to the next one. So I can see we've got quite a few people interested live as well as pre-submitted, but people are curious about the newly discovered Winchcombe meteorite. So Helena, I feel like you're the best person to talk a little bit about this. Could you tell us a little bit more about what's been going on there?
Of course. So I'm super duper lucky that I'm actually curating the Winchcombe meteorite. So I can let you know what's going on. So for those of you that weren't aware, on the 28th of February, there was a really bright meteor, a really bright shooting star observed in Gloucestershire. And we thought, based on how bright it was, that it was quite likely that some of the material that had come through the atmosphere survived and actually landed on the ground. And we were right. Some very competent computer modelers came up with an amazing strewn field. So I was sent out to a field in Gloucestershire to search for meteorites, which is not my natural habitat, but you know, it was great. We did find some material, and we found about half a kilo of space rocks. We brought them back to the museum, and I spent the past couple of weeks having the absolute joy of weighing them all and making sure that they've been stored properly. And the great thing about this meteorite is we know exactly how long it's been on Earth for, so we can basically do some really quick analyses and get some really accurate measurements of things that normally in most meteorites would have like been lost to time, basically. So it's going out to researchers nationally around the country, basically, to try and calculate some of these really important early questions that we might be able to use it for. So it's really exciting. Yeah.
So someone was asking what sort of testing is going to be carried out on it and what do you expect to find out? So what are these sort of questions that you're looking into?
So the meteorite itself, it's shaping up to look like quite a unique, special meteorite. it looks as though it's made up of lots of water-bearing minerals. So it looks as though wherever it came from, whatever asteroid it might have come from, looked as though at one point in its past it might have had water on it. So that's really exciting, because anything to do with water in the solar system is, you know, super duper exciting. So that's one of the things we're going to be investigating. So we're going to be basically taking small bits of it and working out exactly what it's made up of, and trying to come up with its history. So yeah.
Fantastic. So that's what's going on with that meteorite.
It's
amazing.
Very exciting.
Yes, it is. Absolutely. Okay, and more sort of current space events. We had someone asking about the Mars rover, the Perseverance, and what Perseverance has been up to on Mars. So can anyone jump in and tell us a little bit about that, maybe? Tris, do you?
I can say something. Well, so I'm actually not involved in Perseverance, but I was involved in a mission 2 years ago that landed on Mars. And Perseverance landed, what, do you know, Catherine? A month ago, was it? 2 weeks ago?
It's about a month ago now, yeah.
So they probably haven't, they probably have, you know, just started checking out most of their instruments, checking everything's safe and working correctly. That's what we were doing anyway 2 years ago when the mission I was involved in landed InSight. I think I read in the news recently that it's only just started switching on its wheels and roving around. So it's obviously doing all its checkouts.
Yeah, so it's moved around a little bit, and I think you can, if you look on the NASA website, you can find videos of them shooting their laser. You can hear it going, and it sounds very different than what you would imagine a laser kind of sounds like on Earth, just because of different atmosphere and all that kind of thing. I think somebody in the Q&A asked if they had found water yet. They have not found water as of right now with Perseverance, but they did land in a delta, which is a structure that's left over when you have water flowing out of a river. So if you think about, one of the biggest ones is the Nile Delta here on Earth. So this is a structure that's known to come from flowing water. So that's why they went there.
Yeah, previous missions have found water on Mars, right? What was the one with the claw? Phoenix. Phoenix found water buried up into Mars.
Cool. And we've got another Mars-related question here in the Q&A as well. Someone asking, how does Mars have tectonic activity even though it has a solid core? So I know that was something that InSight was looking at, wasn't it? Mars quakes. Am I right with that?
Yeah, you're right. Yeah, so InSight is 2 main instrument packages with both seismometers. There's several ways. One way we were expecting before landing was impacts. So meteorite impacts hitting Mars would create vibrations that we could pick up. As far as I'm aware, we haven't picked up any, well, as far as we're aware, we haven't picked up any meteorite impacts yet. But what we're mainly picking up are local events. So there's still some local geology and geochemistry going on. So another mechanism would be that as Mars is cooling, because it's an old planet now, and it's shrinking down, it's cooling down. As it cools down and getting smaller, you can imagine the surface is buckling a bit, and that's creating tectonic activity that we're picking up.
Brilliant. Okay, so from Mars, move on to sort of general space questions. So one that we've had a lot, or very similar to, is something along the lines of, is there any life out there? So I think, Bertie, your talk was very much about this. So that was not last week, but the week before. So if you missed that, that's going to be on YouTube very soon. But Bertie, do you want to say something quickly about life out there in the universe?
Well, yeah, I'd recommend watching the talk from a couple of weeks ago, and I go into this in a lot more depth. But I mean, ultimately, it's a numbers game because we haven't detected life yet, at the moment, the sort of key questions are around trying to work out what the probability of finding life is. And this depends on many things, like the number of stars in the galaxy, the number of the number of planets around each of these stars, how many of these planets are habitable, and then what fraction of these habitable planets go on to develop life, and also whether this life is microbial or whether it's or whether it goes on to develop advanced life. And we're beginning to be able to answer these questions now. And yeah, if you would ask my personal opinion, I think, in all probability, there probably is life in the universe, but I mean, my guess is as good as anyone's. I think just that it's a highly uncertain question.
Can I ask Bertie a question?
Go for it.
Go for it.
What do you think is more likely that if let's say life is out there, do you think it's more likely we'll find it first in our solar system or on an exoplanet?
I think, it's an interesting question, because obviously the numbers game, it would imply an exoplanet, but obviously it's far harder to detect it on an exoplanet. I think I would say that if we ever detect life convincingly, probably within our lifetime, I think the most convincing detections will be within our own solar system. I think in terms of life detections, I don't think we can realistically be able to expect to detect life probably any earlier than 2040, 2050, those kind of times. The only way we could really detect life outside of our solar system would be to look for gases in an atmosphere that only life could produce. So recently there was a big thing about, is there life in Venus? Because they thought they'd found phosphine in Venus. This turned out to be a mistake, or at least now it's now looking less convincing that there is in fact phosphine on Venus, but but this is the way we could potentially do it on exoplanets, is look for these gases like phosphine in an exoplanet and then conclude that there must be life there from that. So I'd be more convinced if we find it within our own solar system, probably.
Interesting. Thank you.
Good question from within the panel. Brilliant. So another question about finding life out there that a few people have asked. Why do we have to find alien life when we have a perfectly good Earth here? Like, why are we doing this in the first place? Does anyone want to answer that one?
I'll take that one again. So it's kind of like a lot of science. We want to do it because it's interesting, and I think it would have massive ramifications for society. I mean, just the knowledge that there is life out there is truly something everyone wants to know. I feel like everyone just has this intrinsic desire to know, are we alone in the universe? And we maybe don't have to do it. I mean, it's just one of those things that you just want to know. It just have massive implications for society in general.
And even if it's like a different form, right? Like, we're all carbon-based here. What if it's a different element somewhere else? Like, how could we even figure that out? That would be really interesting.
Yeah. Does anyone else have anything to add on that?
No, I think Bertie and Katherine summed it up really nicely.
Yeah, that's a good summary.
Brilliant.
Why not?
Thanks for your friends.
Good question. Okay. So another good question that's come through the Q&A here, that maybe multiple of you might like to jump in on. What are the next major developments or discoveries in astrophysics that are likely to occur in the next few years? So what are your thoughts on that? Who wants to start?
Something to do with exoplanets, right, Bertie? Probably.
In the next few years, probably in exoplanet science, I guess the big breakthroughs in the next few years are we'll be able to detect compositions of many exoplanets rather than just a few. So we'll be able to start kind of doing exoplanet statistics rather than just sort of looking at individual planets, and that'll be a big breakthrough. And we'll understand a lot more about exoplanets then. With James Webb Space Telescope, we'll start to be able to probe a more habitable zone exoplanets. So there's an enormous amount of observational time devoted to that. So actually, looking at further out planets. So I think that they're probably the things I'm most excited about for exoplanet science in the next few years.
Cool.
Tris wants to be. Oh, go on, Tris. Go on, okay.
I'm just going to go round again. Tris, what about you for your area?
So we've got another mission going to Mars, the Rosalind Franklin rover, which is part of the ExoMars string of missions that are going to Mars from ESA. The UK is actually quite heavily involved in that mission, and that's going to be hunting for past habitability signs of life on Mars. That'll be landing, I think, in a year's time, certainly within the next 2 years. And then at Oxford, we're building a mission called Lunar Trailblazer, which is going to the moon to help map where water might exist on the moon's surface, as well as a whole bunch of other science topics. Actually, Katherine gave a talk about this. I think it's up on YouTube, right? So there's another plug there. Go and see Katherine's talk from the first week. And that should be going, maybe a bit of a stretch in 2 years. 2024 is its earliest launch opportunity, but that'd be very exciting. Be one of the first times when we have high resolution maps of where we think water ice is at the lunar surface.
Nice, nice. Helena, what about you for your area on space rocks?
So a bit like Tris, we've got a number of missions also kind of like in the pipeline as well. So most of the space rocks I look at are, the meteorites I look at come from asteroids, which are basically small rocky building blocks of planets sort of things. And there have been a few missions that have gone to them recently. But in the next 10 years, there's going to be some that go to, there's an asteroid that looks like it's made entirely of metal. And they're going to go to that, which I think is super cool. They're also going to be going, there's a group of bizarre asteroids that are in the same orbit as Jupiter. They kind of follow Jupiter in its orbit. And we're also going to be going to visit those, which is really exciting. So that's, I guess, what's happening in my field, because that's going to be really useful. But I think one of the other things that's going to happen is the increase of human space travel, probably in the next couple of decades. That's going to be taking off again, possibly, with obviously America's new initiative to return to the moon, probably Mars at some point before 2100. So, you know, I think that's also going to be quite exciting, getting people back out there.
Brilliant.
I think I would agree with Helena. The Psyche mission sounds really cool to me.
It's called Psyche. How cool is
Yeah.
that?
Well, there's a couple others that are going to different moons. Hopefully going to Titan. That'll be really cool. Yeah.
Forgot about that one.
Arrival of Bepi Colombo at Mercury. That'll be really interesting as well. That should be 2025, I think. So a lot of good missions going to explore our own solar system and find out more about how the planets or moons in our solar system are formed, and what could be there. There's a lot of really cool planets in our solar system to explore. So I'm excited to see the results from that, about rocks, about maybe ice, and sub shell oceans, possibly, if we get to some of those moons. That would be cool.
Amazing. So we've got lots of upcoming missions that can have some very exciting discoveries and results. Fantastic. So everyone stay tuned for that. Keep your eye on those missions. Brilliant. Okay, so let's move on to some more general questions. So one that we had pre-submitted is, I think, Helena, you were going to answer this one. So if our planet used to be covered in lava, how did water come onto Earth? So I think you said this was basically your PhD, right?
Yeah, so I saw this question come up and I was like, oh my goodness, this is great. So the first thing you have to remember when you think about water is that it doesn't always have to be a liquid, right? You can have water in lots of different forms. You can have it as a gas, you can have it as an ice, but you can also have it where water is made up of two H molecules, two hydrogen elements, and one oxygen element. But those can split up. You can have the hydrogen and the oxygen combined into completely different things that can then recombine back into water again. So, you can have a planet covered in lava, and it can have hydrogen and oxygen maybe as part of the lava, some of the gases that are being produced by the volcanoes, things like that. So it doesn't mean that water isn't necessarily present. It just means it's in a slightly different form. But the thing that's really interesting about this question is actually that Earth is a weird place because it's got lots of water on it now, but it shouldn't necessarily, based on where it is in the solar system. So when Earth was forming, it formed too close to the sun. It was too hot to have water ice as part of the material that was building it up. So we actually think it was dry, completely dry. There wasn't even any of that hydrogen and oxygen in different forms, or maybe there was a bit, but not as much as there is today. So we actually think that the water might have been delivered to Earth from some body, some comet or asteroid or something that formed really far outside in the solar system and that traveled forward and impacted the Earth as well. So there's actually kind of two layers to that question, which is why I thought it was really interesting. So yeah, exciting stuff. And the Winchcombe meteorite might be representative of the sort of material that could have brought water to Earth. Little plug there. So yeah, very exciting.
Do you think there was just a big ice ball then?
A big ball of ice, just massive ball of ice just impacted Earth. No, I think probably the stuff that impacted it was a bit like how I was saying, the water, that hydrogen and the oxygen bonded into the rock itself. And then when that landed on Earth, it probably interacted with the material that was on Earth and then recombined back into water as well. So, yeah.
There was just one impact, not lots.
Well, I mean, in the early solar system, there was a lot more impacts. There was many more impacts on Earth. And you can see that when you look at the moon, right? The moon has so many, you know, other people in this panel know more about the moon than I do. But you can see there's like an uptick in number of impacts on the moon at a certain period of time when the Earth was still, and the planets were still kind of forming. So it's not unreasonable to think that there were loads of impacts on Earth delivering this kind of material. So, yeah.
Okay, nice. So I found a really cool question in the question and answer box.
Yeah, thank you for asking that.
Makes you feel validated, right? all your research was useful. Excellent. Okay, so another question in the Q&A box here that I've found that sounds quite interesting. Speaking of the moon, what would happen if we had another moon? So if there were two moons orbiting Earth? Someone want to jump in on that?
Disaster.
The tides would be very weird.
Pretty cool.
I mean, it would depend on the size, I guess, right? The size and distance from Earth.
Say it was like another moon, the size of the moon.
Oh.
Yeah, the first thing would be the tides would be completely different, right? I don't know how it would work in orbital dynamics. I'm not enough of an orbital dynamics person. Would they eventually collide? I don't know.
I feel like that's something that you'd have to get someone who does a lot of modeling and orbital modeling to kind of put in on their model and mess about with and see what would happen.
Because the moon is also something called tidally locked to the Earth, right? So you only ever see one face of the moon. There's a far side and a near side. You've only ever seen the near side, the same side that faces Earth all the time. And that's because after a period of time, the two bodies orbiting like that will become tidally locked. So if you imagine the moon rotating on its axis like this and the Earth spinning, they rotate at the same rate. So the two, you only ever see one side of the moon. So I don't know if you introduced another moon, whether that would force one to become untidally locked. I don't know. It's a very fascinating question. Maybe someone's looked into it.
They would pull on each other too, right? So
yeah.
I mean, Earth and the moon is a very weird system anyway, because the moon is so big for a moon. So like, I don't know, if you think about other planets' moons, they could pull on each other as well, and you could get really weird things happening.
Yeah. So yeah, the other thing to that question is I think we do have a second moon. It's very, very small though, right? I don't know much about it.
Isn't it like a pseudo satellite though? So it actually isn't orbiting Earth, it's orbiting the sun, but in a way that makes it look as though it's kind of half orbiting the Earth a bit.
Oh, you saw that talk as well, yeah. That one. I think it came up on QI at one point as well. But yeah. But I don't know the name of that. I'll Google it.
Cool. Okay, so I can see we've had quite a few questions. People are interested in how we can potentially travel within the universe. So someone here has asked, can we create a wormhole? So do any of you guys know anything about, wormholes? And another question asking, can you warp space-time to move through the galaxy? So this all seems very theoretical to me. So I don't know, how does it hold up in practice, do you think? Anyone want to comment?
All of us are too scared.
I was Googling the other moon on Earth.
I think I saw something about a wormhole experiment recently, but I wouldn't know enough to talk about it.
In the same way, the idea of warping space-time, we do. Every mass does warp space-time.
What?
So it's just the idea that it's a different model of gravity. So you're probably familiar with sort of Newton's law of gravity, where sort of all masses attract each other. There's an alternative, more precise model of gravity where we live in this 4-dimensional space-time, and all masses warp this space-time. And yeah, that there is an idea that you could potentially warp it to speed your way through it, but I couldn't comment on how doable it is.
Because I feel like that's something that if we were to travel to these exoplanets, Bertie, that you're kind of interested in, that's something that we'd have to consider, isn't it? Because they're so many light years away.
Yeah, that certainly would make it a lot easier if we could, yeah, build some kind of way of warping space-time and make the trip faster. Yeah.
I saw that someone was asking if it, how would it be possible to travel close to or at the speed of light as well, which is another good question about space travel.
Yeah, so close to is potentially possible. The engineering challenges associated with that are very, very difficult. But certainly it might be possible to build like maybe not a person-sized spaceship, but a very, very lightweight sail that we could possibly get close to the speed of light. So you'd build a very reflective sail and you shoot a high-powered laser at it for a long period of time, and it would accelerate and get faster and faster and faster until it got close to the speed of light. Then maybe that kind of object could get to another solar system, but there are many, many engineering challenges to overcome before we'd be able to actually do that. But that's conceivable and possible.
Okay. So if we ever want to travel to exoplanets, this is the sort of technology that we need to try and develop. Brilliant. Okay, and kind of, oh, sorry, go on.
No, I was just saying, I think somebody asked about if we could get to one in our lifetime, and I think right now the answer is no, right?
Yeah, I think I'd probably bet no, unfortunately.
We'll keep our fingers crossed though, just in case.
What do you think could be a reasonable time that we might be able to? Now, maybe not our lifetimes, but in 100 years, 200 years, I don't know.
Maybe, yeah.
Who knows? Hard to say at this point, isn't it? It'd be very exciting if we could, but yeah. So kind of along a similar vein as well, we had another question asked. In an ideal world, how long would it take before we can build a sustainable human settlement outside of Earth? So in an ideal world, how long would it take before we could live on another planet? And in reality, how likely is that to happen? So any thoughts on that one?
Well, I think we could do it now. The problem is money and organisation. You know, it takes a huge amount of investment to, if we were to we could set up a human base on the moon. I mean, we've shown that 40 years ago we could travel to the moon. But the problem is that you need, a huge amount of wealth. It took a huge amount of money. Do you know what the figure is, Catherine, for the Apollo missions? How much of the
I don't know, but it was an obscenely large
2% or something of the whole of the money made in America, right? So, and you just need a lot of investment, and there's ethical questions there as to whether that money is better spent elsewhere, or whether there's need to set up a permanent human base on Mars or on the moon.
But I think
the technology's there, right?
Yeah, the technology's there.
There's a lot that you need to figure out still, but I think they're talking about doing a moon base, and I think that could probably be within less than 20 years, maybe, if they really got on it.
Because like the International Space Station is a big kind of demonstrator that we are sort of able to do that. I mean, most of the engineering challenges associated with going to the moon are, to building a sort of a base outside of Earth, we've kind of already overcome with the International Space Station. And that's been sustaining life for, having a continuous presence up there for a long period of time now.
Isn't that the idea of this Artemis program that NASA or that America is looking to do, is to basically put like an International Space Station around the moon, but like a tenth of the size, that all the astronauts would just have to be like squished in with all the other astronauts? But that's the plan, isn't it? Because we've shown that we can do that, but it's expensive. And it needs a lot of resources and a lot of backing from people. And there is a lot of other stuff that, like Tris said, where does that money go?
Yeah, I mean, the Apollo space missions were basically driven not by science, they were driven by the Cold War. America wanting to get to the moon first before the Russians, before USSR. And now that's gone, there's less of an urge, I guess. Yeah. I googled that.
I think it's fair to say though that it's not, I think that comes up a lot, we're just wasting money to send stuff and throw it at other planets, like with the rovers and things like that. And I do want to say that, we're not just sending money to a different planet. It's investing in a lot of research and technology that we use every day. And it's, paying our salaries and that sort of thing, paying people to work and to live here on Earth.
Yeah. I mean, one of the main examples, one of the examples people keep using is Velcro. Velcro wouldn't exist without the Apollo mission. And another one I learned about recently was studying meteorites, discovered lead poisoning. That's how lead poisoning was discovered. And that it was due to studying meteorites that lead-based paint was banned. So, there's lots of all these kind of things that come out of it that we need. So.
And I think another aspect is, if you think about living on another planet, what do you count as that as well? Is it having a bubble on the surface of somewhere else, or is it actually being able to live there? Is it some kind of terraforming mission? That's much farther off, I would say. So how sustainable would an outpost or something like that be? I think that's really part of what you have to think about.
Brilliant.
That's what we're doing. That's why we're so excited about finding potential water on the moon surface, right? So we can use that two ways. We set up a moon base. We can utilize the water for drinking, and then, but further in the future, we can use it as a refueling station for going on further into the solar system.
Yeah.
So what do you think is more promising, the moon or Mars for this sort of outpost?
Oh, the moon is more likely to happen in our lifetime again, because it's easier to get to engineering wise,
and also arguably more useful. Like, we could then that could be used as a base for further solar system exploration much more easily than Mars could be. So
yeah,
but it is a much harsher environment, which is really interesting in a way.
You get this beautiful view of Earth, though. That's quite nice. Quite like the idea of that out the window in the morning.
You can still see Earth from Mars.
Oh yeah, but like
it's just a little speck.
Yeah, they make a great photo.
Brilliant. So we all want to wake up in the morning on the moon with a nice view of Earth outside our window. That's the dream.
But that's another sad thing about it, is that probably the best way to build a settlement on the moon would be to bury it underground, so you wouldn't even get that. So yeah.
Cool. And on that note, I think we'll get to some more general sort of space science questions. So someone in the Q&A has asked about dwarf planets. So how small are dwarf planets, and are they near the sizes of moons? So how do those two things compare?
So I can have a go at answering this. So our definition of a planet isn't actually based on size. It's size comes into it, but it's not based on size. So it has to qualify three things to be called a planet. A body does. It has to orbit the sun. It has to be what we call it in hydrostatic equilibrium, but basically what that means is it needs to be a sphere, it needs to be round, it needs to kind of balance itself. And the third thing, which is the one that something like Pluto hasn't done, is it needs to clear its neighborhood. So its orbit needs to be basically clear of debris. And those are the three things that qualify it. So something like Pluto doesn't qualify that third one. So it's been downgraded, but that doesn't actually mean that its size has come into it. So I think Pluto is about like 1,000 kilometers in diameter, something.
I think it's like 70% of the moon, basically. It's smaller than our moon. So
that's the thing. So Pluto is smaller than our moon, but our moon doesn't orbit the sun, so it's not a planet, right? Mercury, I think, is also small. That's about 2,000 kilometers as well. But something like Ceres, which is an asteroid, or it used to be an asteroid in the asteroid belt, is now also classified as a dwarf planet. And that's about 500 kilometers in diameter. So it's also significantly smaller than the moon as well. So size is less of a kind of defining criteria for what makes a planet a planet or a dwarf planet or a moon. So yeah.
That's interesting. I did not know that. Cool. So another space sort of question. People were asking in the pre-submitted questions about how you name stars. So how do we go about naming things like stars?
There's a committee, right?
I think so, yeah. There's an international committee, International Naming Star Committee. Well, I don't think there's a naming committee.
Can't you like buy a star to name yourself?
Yeah, I think you can actually.
I think it costs
Yeah,
about 30 quid. I think you could do it.
Yeah.
There's so many.
But the official names go through a committee.
Yeah, the International Astronomical Union.
They also name planets and stuff as well, don't they?
Yeah, I think they help pick the themes for the planets and everything, and you have to get your sites approved.
Could you ever have a star or a planet named after you if you discovered it?
Yeah.
I think planets were named after goddesses,
gods.
right? Like Roman gods
Yeah.
or Greek gods. So I don't know if you can plan.
But like the Kuiper belt, which is this kind of a belt of leftover material that's out past the orbit of Neptune, that's named after Mr. Kuiper. So, you can.
They definitely name asteroids after people.
Oh yeah. That's
I
the
know they
dream.
about that. Yeah, find yourself an asteroid and then.
Yeah, International Astronomical Union, I'd like an asteroid named after me, please. Thanks.
Yeah, they often name after people that done work in the field.
Yeah, my the head of my research group at the museum has got one named after her.
Oh, that's really cool. So is that your dream, Helena, to have a space rock named after you?
It's my dream.
Amazing. Okay, so we've had loads and loads of space questions, but I did want to, before we go, I did want to touch on the sort of how do you get to study and work in space science or astrophysics? Because I know a lot of people have been asking those sort of questions. So what I thought might be nice, just to kind of introduce this sort of last section, is if we could go around each of you and just say a little bit about how you came to be where you are in your field. So kind of what you studied, how long it took, and kind of where your job is in terms of kind of, is it more engineering? Is it more sort of theory? Kind of, do you do practical stuff? Do you sit on a computer all day? Like that sort of thing. So let's reverse the order. Let's start with Katherine this time. Sorry.
So I guess I'm from the US, so high school is a little different. We don't really focus so much. So it was just kind of general science in high school. But for undergrad, I have an Earth and Planetary Science degree, which is not super common. I think that's why I went to that school, is because they offered that and a lot of really cool programs. I was originally interested in astrophysics, but then I fell in love with geology as well, so wanted to combine that together. And yeah, do some rocks and maybe have a chance to be in the field instead of just always on a computer and that sort of thing. And then I did my PhD in geosciences, but with a planetary concentration. So looking at the moon and how different properties of rocks can affect our interpretation of the measurements that we get from remote sensing data sets. And that's what I continue to work on here at Oxford.
Nice. Helena, how about you? How did you get to be a space rock babysitter?
Space rock babysitter.
I'm not going to let that go. That's going to be your job from now on.
That is actually, I quite like the idea of being a meteorite secret keeper. I think that's quite a good name as well, but I'll take babysitter as well. I did normal GCSEs. I did do triple science, and then they're not called GCSEs. They are called GCSEs.
They're still GCSEs. They're just not given letter grades. They're given number grades.
Okay, yeah. So I did, but do they still split into double science, triple science, but you still do all three. I'm not sure, but
broadly speaking, yeah, I think
I
so.
basically did as much of the science GCSEs as I could. So I did the triple science GCSE. I didn't do further maths or anything like that. I actually hated maths throughout school. To be honest, still kind of hate maths a bit. So I did normal maths. For A-levels, I did chemistry, physics, maths, and then biology AS. So I think now with the IB, you can do more, you can play around with your options a bit more, maybe do a bit more, something else as well, which I would have quite liked to have done something other than science, possibly if I had the opportunity to. At undergraduate, I did geophysics. So a bit like Katherine, I didn't want to do physics. My reasoning was more that I didn't want to do the maths. I didn't think I was good enough to do the maths. So I decided to study rocks and things instead, because rocks are great. And then I did my PhD in planetary science, but more specifically meteorites themselves. So what I did was basically look at how we can link meteorites on Earth to bodies that are still left out in the solar system by looking at the way that light reflects off them and things like that. And then I because I was based at the museum for my PhD, I was in a fortunate enough position that I could then go and babysit the rocks. So afterwards, so yeah.
Brilliant. Okay, so kind of two sort of geology routes. Nice. Tris, how about you?
Well, yeah, so at school I did fairly normal GCSEs, I guess. I did double science. Yeah, that's all my school offered at the time. Then for A-levels I did further maths and physics, so pretty much the opposite of Helena. And then for undergrad I did engineering, electrical engineering. I thought that was all right, but I decided I wanted to do something more physics-based. So I just Googled planetary PhDs. And I was quite lucky. Top hit was Oxford, and so I applied to the PhD that I ended up then accepting and getting on. And that's how I ended up getting into this sort of stuff. And my PhD wasn't meant to be building space hardware. It was actually looking at data from space instruments. But I think because I had a background in engineering, people in the physics department kept approaching me with engineering problems. And so I ended up just snowballing in a whole load of other different directions. That's how I ended up where I am.
Nice. How about you, Bertie?
So I did triple science GCSE, then followed by A-levels where I did chemistry, physics, maths, and further maths, and then physics degree, which I did an integrated 4-year MPhys, and then yeah, PhD, which is where I am now.
Excellent. So we had quite a few questions asking kind of how long does it take you to become an astrophysicist? So, I mean, broadly speaking, undergraduate degrees, kind of 4 years or so. And then what about PhDs? How long did everyone's PhDs take? Or I mean, Bertie, you're in your second year now. So how about the rest of you who've finished? Helena, you just finished. How long did yours take?
I'm just trying to work it out.
3.5 years.
No, a bit more than 3.5 years, very nearly 4 years. But like your undergrad course can also be 3 years long. I think most of us in the call probably chose to do an integrated master's, which is an option at some universities where you can stay on and do a master's degree kind of incorporated into your undergrad degree, which is a really nice option if you're interested in research or something like that as well. So it was 4 years that, and then I guess nearly 4 years. It was about a month off 4 years for my PhD.
Katherine and Tris, were yours about the same?
In the US, it's typically 5 years. So that's how long my PhD was. We kind of do things a little differently. So we have classes, and then we have our main body of research. So but it's usually combined. So you don't always have to have a master's. So like I didn't get a master's degree. I just went straight to a PhD.
And Tris, same for you with Helena? Is it very similar?
Yeah, my PhD took 3 years and 364 days.
Seems to be a consistent theme in the group, doesn't it?
In the UK, the research councils that fund PhDs like it if you finish within 4 years. So that's typically what the limit ends up being. But normally it's between 3 and 4 years.
Yeah. It can be longer if you study part-time. That's the thing with a research degree, is there's no fixed time that it can take. I mean, that, like you say, the councils like it to take a certain amount of time, and of course you wouldn't want it to stretch out over 10 years, because by the time you finish, what you started doing will be completely out of date. But it's a lot more flexible and free than the sort of undergrad, which is quite nice. And so I know quite a few people were also asking, how can you work for a space agency like NASA? So who wants to offer some insight?
Isn't the only person that can work for NASA in this call Katherine, basically, officially?
I think you don't have to necessarily have.
I asked them. I remember at LPSC, which is a big conference that we go to every year, going up to the NASA jobs panel and saying, "I'm a Brit, can I work for you?" And they were like, maybe best to go through your own space agency. So we have a European Space Agency, and they said the best way to do it was to work through collaborations with that. So,
to be fair, ESA said the same thing to me. But I think if you look into like internships or courses or things like that that are offered by the space agencies, you can often find things that are not necessarily citizenship required or limited. But so I would advise to definitely, see what's on offer, because there's a lot of different things. And honestly, I've seen some advertisements recently that I'm like, oh, I wish I could do that. But it would be, I definitely encourage everyone to get involved. And if you are super interested, look at local universities like, or like here even, and see if they offer any kind of job or internship or thing like that, where you can see if you can, kind of just sidle into working on some kind of mission.
Yeah, or just email around. People are quite responsive to, they want people to be enthusiastic. So
I think you mentioned something that's really key there, is collaborations. So through, like, there's a lot of collaborations. I know I've learned from you all that the European Space Agency collaborates with NASA a lot. So you can kind of end up working indirectly with NASA, if not directly for them, because of any sort of citizenship requirements. So I think that's something to bear in mind as well. Another question, just a final quick question about this sort of studying and how to become a space scientist. Is a PhD necessary, or can you get into it from other routes?
It depends what you're doing. We're talking about quite a wide range of opportunities here. Working for NASA could mean a whole host of things. You could work for NASA as an artist or an outreach officer or a scientist or an engineer. And it depends what job you're going for and at what level. You can definitely get involved in the space industry without having a PhD. I know loads of engineers that are, I know engineers that have gone to work for JPL that have been British. So it is possible to go and work for NASA as a non-US citizen.
Cool.
I don't know if anyone else has anything else.
Yeah, you definitely. I don't think you do. I think there's the science that we do is quite a narrow field in, like Tris was saying, a much broader set of industries. And even, I don't think you need to do a PhD to do what I do. So to do curation, you can go through a number of routes as well. So you could go study museum sciences, you could go get specific apprenticeships at, for example, the Geological Society or something like that. You can become an accredited member of that and, go about it that way, do more vocational degrees, things like that as well. So, yeah.
And with, with us becoming more involved in space, I think, Helena, you talked about this earlier, maybe space policy is going to be a new important thing. So if you guys want to help promote you know, space in politics. That's also something that we need. We always need people to help represent and encourage, you know, funding for science and all that kind of thing. So that's another way you can go about it and still be involved in space.
And space law as well. That's another
Space
cool thing.
law. Yeah.
Yeah. Lots of interesting questions about, you know, who do these bodies belong to? You know, lots of really interesting questions you can do there. So, lots of cool stuff.
There's so many different routes into space-related careers. So that's really cool. So hopefully that's giving you all at home some food for thought if this is what you're interested in going into. And so I think we'll end with just one final question that I've seen in the Q&A that I think is a really nice one to end on. What is your message to young people interested in physics? So should we go around again? Who wants to kick things off? A message to young people interested in physics. Or space in general, I suppose. Not all of you, I mean, you've got geologists and engineers sort of thing here, so very broadly. Bertie, do you want to start again?
Sure. I mean, I guess there's plenty of information out there about physics. I mean, there's all sorts of great like YouTube videos. If you're like, you know, things like I remember before applying to university, I watched things like Minute Physics and channels like that, which are really great ways to engage with, like, yeah, to understand some like really like they're great and that they like handle some pretty hard physics but in a way that's very accessible. And yeah, if you find some interesting physics books, and yeah, just try and learn as much physics as you can, and then yeah, head down the road of A-levels, undergraduate degree, and possibly even a PhD.
Anything to add? What's your message?
Was that me? I would,
Yeah.
well, I have a slight engineering spin on it. You know, don't be afraid to take things apart, to work out how things work. You know, probe things. I think programming is part of the curriculum now as well, but you know, there's loads of online stuff you can do for programming and working out how computers work. That's a really useful tool to have. I program things like on a day-to-day basis. So yeah, probe things, prod things, see how things work.
Fantastic. Helena, what's your message to people interested in going into this field?
I suppose it would be that it's okay if you don't know something. It's a bit like following on from what Bertie and Tris have said, like ask questions, ask people, take your time. You know, you don't have to, this isn't a rush, it's not a race. Take your time learning things and asking questions and enjoy it. You know, don't work so hard at it that you will work so many hours that you end up resenting it. You know, remember why you like the things that you like. So yeah, take your time, ask questions, and yeah, that's what I would say.
That's incredibly good life advice in general, I think. Thanks for the reminder.
It's what I wish that, you know, somebody had said to me.
Yeah.
So.
Yeah. No, that's
Katherine, how about you?
Yeah, I would follow on with that and just say, yeah, go for what you're interested in, and yeah, seek out the opportunities. There's a lot out there, and you do have to look for them, but they're there. That's something I certainly would have liked to have known when I was younger. There's lots to do.
Yeah, don't be afraid to search and email people. As long as you're polite, people won't mind.
Yeah.
Absolutely. And like Helena said, take your time, ask questions. Don't be afraid to try something, and like, so physics is a very broad field, so don't be afraid to go in thinking, oh, I definitely want to do X, but then actually halfway through studying realize I'm more interested in Y. That's kind of what I ended up doing, not gonna lie. How I ended up doing outreach rather than research. So that's, yeah, don't be afraid to fail and try new things, and as long as you're interested in it, keep doing what you're interested in and go for it, is what I would say. So fantastic. So on that note, I think we will wrap up this Q&A. So thank you everybody who came and who asked questions. I'm sorry we couldn't get to all of them. I know I can see we've got currently like 90 or so questions, some of which we've managed to answer. So that was going to be an impossible feat to begin with only an hour to do it, but hopefully we got to as many as we could. thank you so much for coming. Thank you again to our panelists for all that you've done with this series and for answering all of our questions. We hope you enjoyed it, and we hope you all enjoyed it at home.
Live long and prosper.
And just quickly before you go, we have one final little poll just to see what you thought, see if you learned anything from us answering your questions, and if you enjoyed it. So if you have a chance to just fill that in before you shoot off, that would be great. But yeah, thank you so much for coming. We hope you enjoyed it. Things will be uploaded to YouTube as soon as I can manage it. Apologies for the delays. Lots of things have gotten in the way. But yes, so you can catch up with everything on our physics YouTube channel. And if you're interested in any more events from physics, definitely check out our upcoming events. So I'm going to be posting a few links in the chat. No surprises there. If I can click on it, poll is in the way, go away. There we go. So upcoming events link is now in the chat. And if you're really interested in staying in the know about everything, feel free to join our mailing list as well. So the link for that is also going in the chat there. And I'll just say huge thank you again. So from me and all of the scientists here, huge thank you, and goodbye.
Thank you.